Okay. So sorry if the audio quality is a little bad. I'm in the student center right now, recording this, so there might be some noises in the background. But this is the studio worksheet from what day? Yesterday, October 10th. Okay. In both of my studios, we got through both of these first two questions. This first one was true. The idea here was because the matrix is square, we have this tells us that we have n pivots, and so there's a pivot in every column, which means that our solution is unique. That was the idea here. I guess takeaway from this one, since I'm on it, is it's really good to think of these in terms of pivots, especially if you have a matrix and you know stuff about your matrix. And then for this question, we found that it was false because we know I won't write it like that. You know that AB is, what is it, 3 by 2? And so this domain and codomain, they should be flipped because the codomain is always this number and the domain is always this number. So those should be flipped. Okay, now we get to these problems. These are probably the hardest problems on the worksheet, and they may be the hardest problems for me in the entire class. I'll start with 2A. 2A and 2B are very similar. So I'll focus on 2A for now. And again, I did do this in studio, but I want to talk about it again just because I didn't have as much time to emphasize it as I wanted to. So I'm just going to go through each of these. Column space of A. This is good because we know that A, B, X. We can write this bx here. This is just some vector. You do know that it's a vector in the column space of B, but I'm just going to say for now that it's some vector. That's all we need to know. So this is just equal to A times a vector. We do know some things about that vector, but we don't need it for this part of the problem. And now we look at this, we might remember from earlier in the course that matrix multiplication by a vector is the same thing as taking linear combinations of the columns of our matrix. So let's say, and I'm going to write this over here because I'll also use it later. Let's say A is V1, V2, Vn. Actually, I'm going to call these A's instead of V's. Ooh, Golden's playing. Okay. And then we'll call B, B1, B2, up to Bn. Those are the columns. So here, this is equal to V1, which is just going to be the first component of V, times A1, plus V2 times A2. Oh wait, actually I should be a bit more careful over here. A is m by n, so it has n columns. B has m columns, so this should be m. Okay. In any case, this is Vn times An. Okay. Oh, this should be A2. Okay. But each of these guys here or I guess not the whole thing. These A's are columns of A. And so what we're seeing here is that A, B, X, this original vector over here, this guy here, we can write it as a linear combination of the columns of A. And so this is definitely in the column space of A. Okay? The big concept here is that if we have A times any vector, this is always in the column space of A. Okay? So column space of A is correct. Two that are incorrect for sure are null space of A and column space of B. These are incorrect. And the reason for that is, let's see ABX. What dimension is that? ABX. Well, A is m by n. b is n by m, and x is a vector in Rm, so it's m by 1. Again, this one here just means it's a vector. Vectors only have one column. So let's see. These match, so we're good here. These match, so we're good here. This is going to be a vector in Rm because it is m by 1. Okay? And so for column space of A, we were fine because the A is m by n, so each of these vectors were in Rm. I'm going to say these, we might use it later, these were in Rn because B is n by m. But null space of A, that is a subspace of Rn, not Rm. And the same thing with the column space of B, right? Over here, the columns of B are in Rn, so the column space of B is a subspace of Rn. Both of these, and this here, this symbol here is subset, which is similar to subspace, so I'm just using it as subspace here. These are both subspaces of Rn. And so our vector can't possibly be in that subspace. It has the wrong number of entries. So both of those are definitely wrong. Okay? And so the last thing we need to check is the null space of B. Underline the ones that we're doing. Okay, null space of B. Actually, I don't want to call in there. Okay. So in order for a vector, and we're just going to say in order for V to be in the null space of B, we need B times V to equal 0. Okay? And so that means in this problem, our vector that we're considering is ABX. So we need B times ABX to equal 0. Okay? But this is sort of a problem because we don't know anything about X, we don't know anything about B, we don't know anything about A. And it takes a lot to say that that is always 0 because since we don't know anything about any of, well, we know the size of our matrices, but besides that, we don't know anything. And so it takes a lot to say that that product is always going to be 0 for sure. So for example, I can take B equals 1, 0, 0, 1, 0, 0. A equals 1, 0, 0, 1, 0, 0. And then X equals 1, 1, 1. And in that case, BABX would be B times X is 1, 1. A times 1, 1 is 1, 1, 0. This is 1, 1. You can work that on your own. I just did it in my head. Which is not 0. And in order for ABX to be in the null space of B, well, okay, in order for us to select this option here, it has to always be true. And we just showed over here that it's not always true. It could be something non-zero. And so it could be in the null space of B, but it's not guaranteed to be in the null space of B. So this is the only correct answer. Again, depending on what A and B are, it could be in the null space of B, but it's not always. Like if A and B were just 0 matrices, then this would always be in the null space of B, because if we try to do BABX for these two matrices, these two here, then we would always get 0. But since we don't have any information about our matrices or our vectors, we can't say that it's always in the null space. And again, one more time, we could only choose this option if it were always true. But here it's only sometimes true. And then these two are never true unless the matrix is square, in which case it's only sometimes true. So that's our answer here. Okay. I am going to gloss over this next one because it's the exact same justification as before. We've just swapped the order. This column vector argument is still going to work. These two, so that's why this one's going to work because of the column vector argument. These two won't work. Wait, no, not those two. these two won't work because they're they're a subspace of the wrong space again. And then this one won't work because it could sometimes be true, but it's not always true. And so this will work out exactly the same. Okay, so that's those two. This might be good to remember in case it comes up on true false in the future, but here are your justifications. Okay, and now this is the trickiest part, C and D. So I'll do part C first. We want, okay, I'm going to write down again, A is m by n. M by n, n by m. Okay. So we're asking about the columns of A, B. Let's work out what those columns are. Okay. So A, B. Since we're focused on columns, we want to use the definition of matrix multiplication that has to do with columns. So this will be A times B1, A times B2. And how many B vectors are there? How many columns? M columns. A, B, M. Okay. And so now there's a few things we have to notice here. First of all, each of these, they are all in the column space of A. Okay? They're all in the column space of A. Because it's all of A times some vector. We proved up here that A times any vector is in the column space of A. Okay, so these are all in the column space of A. So let's say they were, well, how do we want to say this? We want to find out whether they can be linearly independent or dependent. One thing I'm going to say first is that they definitely could be dependent. That's definitely possible. Because what if B is just like the zero matrix? It just has a bunch of zeros. Then all of these vectors back over here are going to be the same vector. They're just going to be the zero vector. And so they're definitely going to be linearly dependent. We can almost always make our columns linearly dependent if we just pick them to be zero, because zero is always linearly dependent. So that's easy. The hard part is figuring out whether it's linearly independent. In order for all of these over here, I guess I shouldn't be underlining that line. In order for all of these to be linearly independent, we would need a pivot in each of the columns, right? So these would have to have m pivots. Or actually, let's not do this in terms of pivots. If they're linearly independent, this means that there are m linearly independent vectors in the column space of A. All right, we're pretending it is linearly independent to see if it works out. This is an issue though, because A only has n columns. So these two lines are actually contradicting each other. The first line is telling us that there have to be at least, I should say at least. This first line is telling us that there are at least m pivots in A. So A has greater than or equal to m pivots. But this down here is telling us that, well, we only have n columns, so we can't have any more than n pivots. So A has at most n pivots. And the reason that this is impossible is because m is greater than n. And so, like, let's say m is 2 and n is 1. I can't have more than 2 pivots and less than 1 pivot. So this is just going to be impossible. So they can't be linearly independent. If they were linearly independent, our matrix AB or our matrix A would have too many pivots. Okay? So just, again, a recap. Can't be independent because this would force A to have M pivots. But M is greater than N, and A can only have at most N pivots. You could have also just looked at an example here. M is greater than N, so A is a tall matrix, so you could have done something like this, multiply it by B, and just working out an example, this would give you 1, 0, 0, 0. Wait, no, that's not right. 1, 0, 0, 0, 1, 0, 0, 0, 0. Which is definitely linearly dependent. So you could have also worked out a few examples and seen that it's probably not going to work out. Okay. So now we'll do the other way around. You might think that because the order is reversed, this will be reversed. But that is actually not true. So let me just take these matrices that I did up here. I said 1, 0, 0, 0, 1, 0. And I'm doing BA, so I have to move this over a bit. Okay, what is this equal to? This first entry is 1, this second entry is 0, this entry is 0, this entry is 1. Okay, those are definitely linearly dependent. So they can still be linearly dependent. Or sorry, I'm not dependent. Independent. So they can be linearly independent. That's fine. We sort of expected that because the order reversed, so we expected that our answer might reverse. However, like I said earlier, it's very easy to get linearly dependent columns. For example, if I do A is this and B is this, this is just all zeros. So it could also be linearly dependent. This is very trippy. I just want to take a moment to point out how trippy this is. So we know in general that if we swap the order of matrix multiplication, it won't work out the same, right? Because for one, if our matrices aren't square, then swapping the order will give us matrices of different dimensions. This top one is 3 by 3, the bottom one is 4 by 4. So we already know that swapping the order of and as a side note, you also can't swap them if they're square. But in any case, we already know that swapping the order of matrices changes the matrix. But this tells us that it's even weirder than that because we can swap the order of the matrices. You might expect the properties of the matrix to swap also. But this is saying that it doesn't. This does swap, but this doesn't swap. And so that's a little trippy. And I think it's important that you look through this again and try to see if you can understand this in your head. I think this first one, part C, this is maybe the hardest question you could get asked in this class, in my opinion. It is very, very difficult. Very difficult to understand. I wouldn't make a huge fuss about it, but I would sincerely try to understand that. At the very least, this could be a good time to work on the skill of just testing examples to see if you think it'll work. Examples are sometimes useful for answering true-false questions. If you have any questions about this, feel free to email me. Again, this is a very hard question. An easier version could appear on the exam. I would hope not, but an easier version, actually, it has appeared on practice exams. So please feel free to ask me, email me questions if you have any about this. Number 3 is actually sort of easy. So A is this transformation, B is this transformation, C is this transformation. So projection onto the xy plane, ignoring the z coordinate. Okay, that's just... Or actually, I'll do this. Okay. If I take 1, 0, 0, and I apply A to that, I am projecting onto the xy plane, and I'm just ignoring the z coordinates. So that's just 1, 0. I know that A of 0, 1, 0, similar process, that is just 0, 1. And then A of 0, 0, 1 is, I'm ignoring the z coordinate, so it's just 0, 0. You can think of this geometrically. If you take the z-axis and you squish it down onto the xy plane, you're just going to end up at the origin. Okay. This tells me that A is 1, 0, 0, 1, 0, 0. Cool. Okay. U, rotation 90 degrees clockwise. That is negative 90 degrees counterclockwise. The reason I write that is because our typical rotation matrix is counterclockwise, so we need to swap the order. Okay. So that is cosine theta, sine theta, negative sine theta, cosine theta. Okay. Cosine of negative 90, sine of negative 90, negative sine of negative 90, and then cosine of negative 90. Okay. I'll just draw this on the unit circle real quick. Negative 90 is down here. So that is 0, negative 1. So cosine is 0. Sine is negative 1. So that's 0, 1, negative 1, 0. Okay. And then V, I'm scaling in the x direction by a factor of 2. So if I multiply that by 1, 0, I'll just get 2, 0. Because I'm scaling by a factor of 2. But if I multiply that by 0, 1, I'll just get 0, 1. Because I'm doing nothing to the y direction. And V is going to be 2, 0, 0, 1. Okay. And then for part B, computing the matrix for this composition of transformations. Again, reading this out, this means apply T, then V, then U. This is what this notation means. We read right to left for some reason. Well, there's actually a good reason. It's because if we were to... This is just a side note. This isn't super important. If we were to multiply this by a vector, we would do this first. And then this would be some vector here. Then we would do this. And then this would be some vector here. And then we would do this. So that's why the order is reversed. Oh no. I wrote something I didn't mean to. Okay. That's just a side note. Doesn't really matter. To actually get this, we just multiply their matrices. So that's going to be U is B. V is C. And then A. So this is B is... Ah, I see. I called these the wrong thing. I guess actually technically to be the most rigorous, I should do this. It doesn't really matter. Okay. So, B is 0, negative 1, 1, 0. C is 2, 0, 0, 1. And then A is 1, 0, 0, 1, 0, 0. So I will just multiply these out real quick. It doesn't matter which ones I group together to multiply. I could do that first, or I could do this first. Matrix multiplication is what we call associative, and so you can just do that, even though you can't swap the order. So let's see, I'm going to do the left two first. That's going to be 0, 1, negative 2, 0. And that is 0, 1, 0, negative 2, no. Negative 2, 0, 0. Okay. And so that's our final answer. And then if you want to do a geometric interpretation, this is the matrix that forms when you do t. So you project onto the xy plane, and then you scale in the x direction by a factor of 2, and then you rotate clockwise by 90 degrees. Okay. So that's the worksheet. Again, let me know if you have any questions, especially with this second one here. That one is very, very difficult. Do not feel bad if you don't understand it immediately. You may have to think about it for a bit longer. Hopefully the other two were a bit easier to understand. Those two I would make sure you work out until you understand them. With that said, I hope to see some of you at the review session on Monday.